Rutgers, State University de New Jersey. Él tiene su doctorado en física de la Universidad de California de Berkeley, o sea que es bueno, muy bueno.
Go Bears.
Go Bears. Y su área de estudio es la convección tropical, y en particular él trabaja desde modelos simples hasta modelos muy complejos, y también un poco en la teoría. También nos va a acompañar Kathleen Skiro, quien es una alumna de la Universidad de California en Los Ángeles, que trabaja con David Nealon, su asesor del doctorado, y pues trabaja también en la área de convección, y en particular en la teoría de autocriticalidad, que viene de la mecánica estadística, y va a dar una hora de charla sobre eso, y un día me toca a mí y voy a hablar sobre la transición de convección somera a profunda. Algunos detalles, algunos pidieron constancia. Entonces, si quieren constancia, tienen que asistir por lo menos 4 de los 5, yo creo que es la política de la universidad. Okay. Y pues no va a haber tareas ni nada. La verdad, el primer día, bueno, sí, les damos tareas, no es un problema. En las primeras lecturas, yo creo que hoy, a lo mejor en parte de mañana, él va a dar un poco de revisión, a un nivel bastante alta, pero una revisión sobre pues, la convección en los trópicos y un poco de la parametrización de convección. Y luego seguirá más en cosas que él ha estudiado, investigado. Entonces, no hay requisito en ese sentido. Yo quería que pues, quien se interesara viniera, pero el nivel va a ser alto. Okay. Pero si tienen preguntas y dudas, lo que él quiere es que haya interacción. Una de las razones que no quería que estuviéramos en este lugar, que no es lo más ideal para eso, pero siéntanse con confianza de levantar la mano y criticar, gritar, y él, pues todo lo que sea, ¿no? Okay, todo vale, o como dicen en brasileño, vale todo, ¿no? Entonces, no se sienten tímidos, ¿ok? La idea es cuestionar y ver. Me alegro mucho de que pues haya tanto interés en el tema, no sabía. Entonces, excelente, me da mucho gusto. Si tiene alguna pregunta o duda ahora, haremos la constancia al final. Vamos a pasar lista, digamos, de todos los días, y ahí les manda, creo que lo hacemos por email, es lo que me dijo Ivonne. Okay. Entonces, si no hay algo específico de pregunta, podemos comenzar. Nada más quería pues agradecer a la coordinación de ciencia, de la investigación científica, porque apoyaron esto, el posgrado y obviamente el centro, Bárbara y nuestros colegas aquí que están trabajando con el video, entonces, y Yvonne, para variar, con el anuncio y todo. Entonces, si no hay otra cosa. Ajá. En teoría, vamos a grabarlo, ¿no? Y lo vamos a subir. ¿Esa es la idea, Giselle? Sí, y ¿y qué pasó con los amigos de Yucatán?
Ya les mandé la liga y espero que estén bien.
Ok. Bueno, entonces en teoría hay acceso desde fuera, pero tenemos que indicarles a esos grupos, el IP y todo eso, ¿o cómo se hace?
Nada más es una dirección y
Ok. Okay. Bueno, voy con ustedes. Entonces, pero se va a grabar. Entonces, si alguien se interesa después, se puede ver, ¿no? Y vamos a poner el link. Sí, pusimos como un website con poca información por ahora. Cuando vuelva Pietro, ya vamos a subir más cosas, los artículos, los videos y toda esa información. Okay. Y pues, como digo, si tienen preguntas y si quieren preguntar después, Ben va a estar aquí. Vamos a estar andando por acá. Entonces, si alguien también se quiere reunir con él, o con Kathleen, pues, con mucho gusto. ¿Ok? Entonces, ¿sin otra duda? Okay. Bueno, otra cosa, la idea sería como 1 hora o hasta que Ben se canse, y pues nos paramos, tomamos un café, galletas, mucho azúcar, y luego volver y a quemar ese azúcar, ¿no? Okay. I think that's probably, they're obviously very entertained.
Okay.
Okay. Bueno, gracias, Ben, por el esfuerzo. ¿Cómo le hago? Voy a verlo en el video.
Oh, we're good to go. So thanks to Dave for organizing this this course in La Física de la Convección Atmosférica en los Trópicos. That's the only Spanish that I'm going to attempt throughout this lecture. And keep in mind, even if your English isn't very good, it's much better than my Spanish. So, yeah, so the physics of tropical convection, along with, as Dave mentioned, Kathleen Chiro from UCLA. So let's get in and just give you a little bit of an overview. You've probably looked at the course website, but just to remind you what we're planning on covering in this course. So we have 5 lectures. Today we're going to do an introduction, kind of start slow. Spend probably the first hour doing a basic 101 review of thermodynamics for those of you who might be new to the field. And then in the second hour, talk a bit more, kind of do a survey of convection in the tropics. Tomorrow, we'll focus a bit more on theories of tropical convection, at least in the first part of the lecture, and then the second part, which Kathleen will give, kind of follows up on a concept that's related to both her research as well as the theory of tropical convection. Wednesday, we'll talk about tropical convection and its coupling to the large scale, so that's kind of that's one of my areas of interest. Thursday, talk a little bit about how we represent convection in climate models. And then the second part of Thursday's lecture, Dave will follow up on, so the part with Kathleen and Dave, those are intended to be more sort of in-depth topics of research. And then finally on Friday, wrap up with tropical convection in the land surface. That's also another area of interest of mine. And you'll note my little star at the bottom that, of course, tropical convection is very broad. We could talk about many topics. This choice of topics reflects our particular set of interests. Some obviously important aspects of tropical convection won't be covered, namely, probably the most significant one is tropical cyclones, so that, we have to kind of limit what we talk about. Plus, I'm less comfortable talking about tropical cyclones. So, just in terms of the expectations for the course, first of all, hopefully I can teach you a little, the three of us can teach you a little bit about tropical convection, enough to pass the exam on Friday. There's no exam. The second point is to link research areas and topics of interest among the participants. I'm hoping that we'll take advantage of this time together to kind of talk about what we're all interested in and how we might draw connections. And Dave provided me a list of some of the folks here probably in the audience, so you can kind of see some more local folks who are doing various things related to tropical convection. And certainly by the end of the week, I hope to hear what more of you are doing. And the third point really is to stimulate discussion and encourage collaboration. So that kind of follows the second point. So are there any questions so far? And as Dave said, we'll try to break around 6 o'clock for a little mid-session, mid-lecture break, and then hopefully get back quickly, maybe 6:10 or so, to cover the rest. And please feel free as we're talking to interrupt me if you have any questions. So topic 1, or lecture 1, will focus primarily on these two topics. So the first half of the lecture, hopefully half, depends how quickly I can go through one semester of thermodynamics, but we're going to talk about fundamental concepts, definitions, and equations that are relevant to understanding tropical convection. So I want to introduce the kind of terminology that we'll use throughout the next 5 days, so that we have kind of a basis to refer back to. And then the second part after the break, we'll focus more on providing an overview of the observed spatial and temporal, space and time characteristics of tropical convection, and their relationship to our understanding of tropical weather and climate. And that's just meant to be a survey of some interesting things. So many people are interested in convection because of things like this. This is a nice illustration of a very well-developed cumulonimbus hot tower, booming thunderstorm. And when I show this image to my students in class, I always like to say these little guys in the foreground, the little cumulus congestus, they all want to grow up and become the big, cumulonimbus. Not all of them make it, but some of them will eventually grow up and become big thunderstorms like this. And certainly, with the students I teach back at Rutgers, a lot of them are interested in severe weather, and this would be the type of convective event that would produce severe weather over the mid-latitude, over the continental United States in summer. This is kind of what I'm more interested in terms of convection in the tropics, and that's how it looks at the large scale. So this is a satellite image. This is one of my favorite websites, the NASA Image of the Day Gallery. You can go there and be entertained. If you don't want to work some afternoon, you can just spend a whole afternoon looking at nice pictures. But I like this one because it illustrates a lot of interesting features about the cloud field in the tropics. So the most prominent feature of this image is this band, this zonally elongated band of cloudiness just north of the equator in the Pacific. This is the intertropical convergence zone. So we'll talk a little bit later in the week about these kind of larger scale structures. You see South America over here, so they've got kind of convection that's happening. These are sort of cloudy clouds that are associated with convective events that are happening over South America. At higher latitudes, of course, we also have interesting stuff going on. There's a storm track here in the southern hemisphere. We have one that's cut off up here, but a storm track in the northern hemisphere. So looking at an image like this, you can clearly see that there's a lot going on, and we want to try to develop understanding of this large-scale structure in terms of our basic understanding of this process, which we call cumulus convection. And I'd just like to point out here, this is some artwork that my son made for me, pointing out different kinds of clouds. And I would note that he even has them kind of in the relative, if you think of this as the vertical axis, the stratus or the low clouds, cumulus, and then upper level cirrus clouds. We're going to focus primarily on cumulus convection, by which we're considering the vertical transport of relatively warm air from the surface. So essentially, we'll talk a little bit more about this, but the Earth receives input of solar energy at the top of the atmosphere. The atmosphere is largely transparent to that solar energy, so the heating of the atmosphere actually occurs from the bottom up. And so as the surface warms, it generates buoyancy. We'll talk about, if you don't know what buoyancy means, we'll get to it. But those warm parcels of air that are in contact with the surface rise up through the upper troposphere. And as we'll see tomorrow, this kind of cumulus convective process is important for understanding how the temperature profile of the Earth looks like. So just a little background, cumulus convection comes from the Latin word cumulus, which means heap or heaping. Cumulus clouds kind of look like a ball of cotton, which is what this artwork is made out of. And convection means to carry together. So, it's basically this idea of parcels that are being carried upwards, forming these heaping clouds. The physical basis of this process is really simple. As I guess many things often are, you can trace them back to some first physics principle. The applicable principle here is Newton's second law of motion, and that's where this concept of buoyancy comes from. So just to kind of give you the basic outline of buoyancy, we'll first start with Newton's second law of motion. Force is equal to mass times acceleration. Of course, this is a vector equation, but we're really in this course largely concerned with what's happening in the vertical direction, so we can just think of the scalar force in the z direction, or the vertical direction equals the mass times the acceleration in the z direction. So for this idea of hydrostatic equilibrium, we first want to consider a case in which we have an environment. So the environment is kind of this darker blue background, and the environment, for future reference here, quantities that have a prime refer to the surroundings or the environment. And in this kind of view of convection, we tend to think in terms of parcels. So we imagine carving out a little blob of air from the environment, and that becomes our parcel of interest. And so we basically want to understand the force balance, or we want to understand or apply Newton's second law to this parcel. So in the case that we're considering first, which is where we get hydrostatic equilibrium, we assume that the parcel density is the same as the density of the environment. So then we can apply Newton's second law. Of course, we have the sum of forces acting on this parcel going to equal the mass times its acceleration. So the left-hand side, if we have density rho, and we think of this as a little rectangular prism of dimension delta x, delta y, and delta z, then the density times this delta x, delta y, delta z is a volume element, so that's the mass element times the acceleration. And then that's equal to the sum of the forces that are acting on this parcel. So since we're considering this parcel within the Earth's gravitational field, we have a force contribution from gravity, which acts on the center of mass of this parcel. So minus its mass times the acceleration due to gravity g. And then we also have, because this parcel exists within a fluid, and that fluid is exerting surface force in terms of pressure, that the pressure acting on the top face is at P evaluated at z plus delta z. So that's pushing down on the parcel from above, and then the pressure at the bottom pushing up P of z. And so then we can consider the case if we have an equilibrium situation in which the acceleration equals 0. In other words, this parcel is either at rest or moving with a constant speed. And then in the limit where delta z goes to 0, we basically recover this equation, which is the standard hydrostatic equation, which relates the vertical derivative of the pressure field to the density field. So what we're going to consider in terms of the convective process is the more general case in which the parcel density rho is distinct from the environmental density. So if we go through and do the same type of analysis, we essentially get to this line down here, which relates the acceleration in the z direction to the gravitational acceleration, and then that gets scaled by the difference in density between the parcel rho and the environment rho prime divided by rho. And this term is what we call the buoyancy, okay? So when I introduce this concept to my students in thermodynamics, I tell them to think about the little rubber ducky that they have in their bathtub at home. If you push the little rubber ducky down in the water, what happens to it? It bounces up. It bounces up because the density of the rubber ducky is smaller than the density of the water. That exerts a positive buoyancy force, which pushes the little ducky up. If you put a steel ball in the bathtub, the steel ball sinks. It's denser than the environment, the water, and so it would have a negative buoyancy. So this idea of positive and negative buoyancy becomes very important. So that's buoyancy in Newton's second law. So the other fundamental piece of physics is the first law of thermodynamics, and this is also just known as energy conservation, the idea that energy is neither created nor destroyed, changes form. So if we have a parcel of air in the environment, and that parcel of air expands, oftentimes what we're thinking about is a parcel that moves through its environment changes its size. So as it expands, because it's expanding against something, it's doing work. The particular kind of work it's doing is pressure volume or mechanical pressure volume work. And so we can express the differential form of the work, delta W, as the pressure times the differential of the specific volume, alpha. And alpha is specific volume just means it's the inverse of density, the volume divided by the mass. So doing work requires energy. So the question we need to ask is, what is the source of that energy? And there are two primary contributions. The source of energy can either come from the environment, which is represented by a heat flow or a heat exchange between the environment and the parcel. It could also be a stored form of energy, or more generally, a combination of the two. The stored form of energy that we'll talk about is what we call the internal energy, denote that by U. For what we're going to be considering, of course, is a gas, and a type of gas called an ideal gas. With an ideal gas, the internal energy is a very simple function of temperature, so we can express the differential du of the internal energy as this scale factor, CV, called the specific heat at constant volume times the change in temperature. So the basic idea, I mean, the way this CV quantity is actually estimated is you would imagine adding some increment of heat energy to some sample of stuff, measuring its temperature change, and the scale factor that relates the two is the specific heat. Now, it's important here that it's at constant volume, so you're basically, you would do that in the case where you don't allow the volume of the parcel to change. We'll also define a specific heat at constant pressure, which is analogous to this, except in that case we hold the pressure fixed. So when we basically can state this formally, mathematically, in the following way, First Law of Thermodynamics, we have a heat exchange equals a change in internal energy plus some work. So the next concept we need to talk about is an adiabatic process. So what do we mean by an adiabatic process? Well, it's one in which essentially there's no heat exchange that happens between the system and its environment or between the parcel and its surroundings. So in that case, delta Q is equal to 0. Now, as you might imagine, this concept of a parcel is a very idealized thing. In the real world, parcels are abstractions, but it turns out that this adiabatic approximation actually works pretty well for many meteorological applications. And so, even if we're not strictly dealing with an adiabatic process, the architecture that we build in developing adiabatic processes, we can often apply. So we distinguish two types of adiabatic processes. Dry adiabatic, of course, refers to dry air. Moist adiabatic refers to moist air. And the moist situation, as you might imagine, can be a bit more complicated than the dry situation because of the presence of water. And, one of the most important things that water does in the atmosphere is changes phase. So if we have a liquid droplet of water in the atmosphere, it can evaporate. That's a phase change. Water vapor can condense, form a liquid droplet. Those are phase changes. And those phase changes have energies associated with them, and we'll talk about that in a moment. So a concept that we develop as a result of combining this adiabatic process with the first law of thermodynamics, as well as the ideal gas law, basically allows us to derive how the temperature profile changes as a function of height in an adiabatic environment. And this is what's known as the dry adiabatic lapse rate. So dT dz is the temperature change with height, and the lapse rate by definition is minus dT dz. So for an ideal gas, which is evolving under a dry adiabatic lapse rate, the temperature change with height is 9.8 Kelvin per kilometer. So that means as you go up in an atmosphere at the dry adiabatic lapse rate, for every kilometer you go up, the temperature drops by about 10 Kelvin. Associated with the adiabatic process, we can actually define a new thermodynamic variable. This thermodynamic variable we call potential temperature. So the math here, if you want to see that worked out, I can work it out for you at some point. But you can trust me that if you start with the first law of thermodynamics, and here I've written it in a slightly different form than what was on the previous slides, but I can use the ideal gas law in this expression of the first law, do an integration with respect to pressure, and that tells me how the temperature field varies with pressure. And it turns out this particular relationship between temperature and pressure for an adiabatic process, we give a name, which is the Poisson Equation. And it's from this Poisson Equation that we define this variable theta, potential temperature. And the way we define it is so there are two constants of integration, or you think about integrating this from some initial temperature and pressure to some final temperature and pressure. So if we set in this equation T0 equal to this quantity theta, and P0 equal to 1,000 millibars, so basically pressure close to the surface, then this is how we define the potential temperature. And the interpretation that we give to potential temperature is if you imagine you have a parcel that starts up somewhere in the atmosphere at a temperature and pressure, and you lower that parcel dry adiabatically down to 1,000 millibars, the temperature it would have as a result of that dry adiabatic process is potential temperature. Okay? Now the next concept we want to talk about, we want to go back to this kind of parcel view of things, and we want to ask what happens to a parcel that starts at some equilibrium position Z0, and we cause that parcel, which is embedded with its in this environment, we cause that parcel to undergo a dry adiabatic displacement. So we move it from this position Z0 up to a new position Z0 plus delta Z. Okay? So we basically want to evaluate the force balance, or Newton's second law, on the parcel at this new position, assuming that we start from some equilibrium state down here. So I've just rewritten Newton's second law, the acceleration. Of course, that's the first derivative of the vertical velocity. And this is, again, g times the density difference divided by the density. Now, it turns out we can replace this expression for the buoyancy written in terms of the density as either a difference in the temperatures, so the temperature of the parcel minus the temperature of the environment, using the ideal gas law, and then using the definition of Poisson's equation, we can actually relate that to the difference in potential temperature theta minus theta prime. Okay? So then what we want to do is relate, so we're evaluating this acceleration at this new position, but we want to relate back to the quantities that we've defined at the equilibrium position. And in particular, at the equilibrium position, the potential temperature theta of the parcel is the same as the potential temperature of the environment. Okay? Now, the environment is following some lapse rate, which we're writing here in terms of the potential temperature. That's determined by the meteorology or the processes external to the parcel. It is what it is. The parcel itself is undergoing a dry adiabatic displacement. So by virtue of it being dry adiabatic, and I forgot to mention this when I introduced potential temperature, one of the nice things about potential temperature, the reason we go through the effort of defining it, is it's what's called a conserved quantity for a dry adiabatic process. So oftentimes the game in thermodynamics is to find some quantity that's conserved, meaning that its value doesn't change as a result of the process. So for a dry adiabatic process, the thermodynamic variable that's conserved is theta. So if this parcel goes from this initial temperature theta, potential temperature theta 0, to this new position and theta is conserved, then it has the same potential temperature at that point. So what that allows us to do then, knowing both the lapse rate of potential temperature for the environment plus the conservation of potential temperature for the parcel, we can basically rewrite this expression as theta divided by theta plus delta z, so the difference, the displacement delta z, times the change d theta dz. Okay? Then we apply a standard trick, which is we have this theta plus delta z times d theta dz. If dz times d theta dz over theta, or if this is small compared to theta, we can basically do a Taylor expansion. Taylor expansion, remember you have a function, you can expand that function in terms of its derivatives, which allow you to approximate the function to arbitrary order. So first order Taylor expansion basically allows us to simplify this even further so that we have the acceleration in the end is minus g over theta times d theta dz times delta z. Okay? Now, the reason for going through all of this exercise is that leaves us with a particularly simple looking equation. So the acceleration, the derivative of the velocity, is the second derivative of the position. So that we have a derivative, second derivative in position. And this quantity here, g over theta times d theta dz, we call that n squared. We call that parameter n squared, which is the Brunt-Väisälä frequency or the buoyancy frequency. And so we have this second order differential equation, which we know how to solve. Okay? So without really going through this, you can actually derive the similar expression, but expressed in terms of the lapse rate of temperature rather than the potential temperature. The point is, we have this second order differential equation and this important parameter n squared. And so you remember I defined the dry adiabatic lapse rate, the 10 Kelvin per kilometer. So if the parcel is being displaced dry adiabatically, then the parcel's temperature, remember its potential temperature is conserved, but its temperature is actually decreasing. And the decrease of the temperature by the dry adiabatic process is the 10 Kelvin per kilometer. Gamma, without the subscript, is the environmental lapse rate. And so if gamma is less than gamma d, the term underneath the square root here is positive, or n squared itself, if you square this, n squared is positive. And so that gives us solutions to this equation which are oscillatory. That we know how to solve that second order differential equation. And that has oscillatory or sines and cosines as solutions. And so what this tells us is that if the lapse rate gamma is less than, the environmental lapse rate is less than the dry adiabatic, if we displace this parcel away from its equilibrium position, the result of that displacement is that the parcel returns to its equilibrium position. Now, it doesn't actually go back to its equilibrium position, it oscillates. So I can explain that in more detail if you like, but that's basically just an oscillatory type of behavior. More interestingly, from the sort of convective point of view, generally, is when gamma is greater than gamma d. In that case, if you solve this equation, so now n squared would be negative, that has exponential form solutions. So it has a growing exponential and a decaying exponential as the two solutions. And the growing exponential would imply that the parcel displaced from its equilibrium is going to move away from its equilibrium. And in fact, it's going to continue to accelerate away from its equilibrium. Okay? And that describes an unstable situation. Okay. So now we want to change gears a little bit and throw moisture back into the mix. So we have to define a couple of variables of interest. So the first one is the mixing ratio. Mixing ratio is simply the density of the vapor, the water vapor within a sample of air to the density of the dry air within that sample. Oftentimes we don't want to work in terms of density, we like to work in terms of pressure. And so we can approximate, I mean it's a slight approximation here to say that the ratio of the vapor density to dry air density is some scale factor epsilon, which turns out to be the ratio of two constants in the ideal gas law, one for water vapor and one for dry air, times the ratio of the vapor pressure, which we denote by the symbol E, and the total pressure P. Okay? And mixing ratio is conserved as long as no phase change occurs. So if we have some sample of air that's moving along, as long as there's no evaporation or condensation within that sample, mixing ratio is conserved. Now typically, mixing ratio is expressed in units of grams of vapor per kilograms of dry air. So I'd just like to point this out to give you kind of benchmarks for what values we find in the real world. So, in very dry air masses at high latitudes, mixing ratios might be a few grams per kilogram. In moist tropical air masses, 20, maybe 30 grams per kilogram are kind of the upper limit. A related quantity to mixing ratio is the specific humidity. It's just a slightly different ratio, but you basically mixing ratio and specific humidity are equivalent for our purposes. The term saturation refers to how much water vapor we have relative to a condition of saturation. This condition of saturation is essentially when, if we imagine we have some parcel of air that has water vapor in it and it reaches this saturation point, the water vapor condenses. And so we're interested in knowing how to relate how much water vapor a parcel has to the point at which it becomes saturated, and we'll see how to do that in a second. But we distinguish subsaturated conditions, so if the amount of vapor in the parcel is less than what's required for saturation, that's referred to as subsaturated or undersaturated. We can actually have supersaturated states in the atmosphere, although they don't occur that commonly, but it is possible to exceed this saturation limit. So in general, the atmosphere is subsaturated. When we have saturated or supersaturated conditions, that's when we see things like fog, clouds, and precipitation. And this just gives you kind of the molecular perspective. So if you imagine taking a vacuum, some evacuated chamber, dumping some water in it initially, some of the molecules are going to start, there's a distribution of kinetic energies within this liquid. So those molecules are going to start leaving the liquid phase and entering the vacuum up above. While it's in this state of subsaturation, you can see that the arrow here kind of gives the net direction of transfer. So there are more molecules that are leaving the liquid. You still have molecules that are coming back in the opposite direction. It's a random process, but the arrow is bigger here than here. When we get to the saturated point, that's when you basically have an equal, in a statistical sense, an equal number of molecules leaving as you have returning. And this would be the supersaturated case, so we would have, a larger proportion of the molecules moving into the liquid phase from the vapor phase. So I mentioned, water vapor in the atmosphere turns out to be very important, and the reason it's very important is largely because of the phase changes that water vapor undergoes, and those phase changes involve an energy term. So if we imagine the situation where we have some liquid and it starts to evaporate, how do we get it to evaporate? We get it to evaporate by adding energy to it. So this is actually written slightly from the opposite perspective. So if you think about having a liquid that has some kinetic energy associated with it, the molecules have a distribution of kinetic energies. The molecules that are most likely to escape are the ones that have the highest kinetic energies. So as they escape, they tend to take high values of kinetic energy out of the liquid, and what's left over is that the mean kinetic energy of the liquid decreases, and so the kinetic energy is therefore reduced, and this is why we think of evaporation as a cooling process. So if you think about yourself, the way the human body cools is through evaporation. As you perspire, you're basically losing heat energy through the evaporation of water molecules from your skin. So the total energy that's required to convert a mass of substance, and this could be any substance, from one phase to another is what we call the latent heat. And so for water, we have latent heat, so we can go from the liquid to the vapor phase, which involves this latent heat of vaporization or condensation, 2.5 times 10 to the 6 joules per kilogram. And you'll notice, of course, for these other phase changes, we also have latent heats associated with them. But for the solid to liquid transition, the take-home message here is that the latent heat of fusion or melting is about a factor of 10 smaller. So there's a bigger energetic jump in a sense, between the liquid and gas phase than between the solid and liquid. We can go directly from the solid to gas phase, which is essentially combining these two. So how do we determine the saturation of a parcel? We do that in terms of the saturation vapor pressure. So we can characterize the moisture content of a parcel by its vapor, or the water vapor content by its vapor pressure. And we can define this saturation vapor pressure as the vapor pressure at which saturation occurs. So if we're subsaturated, the actual vapor pressure in a sample of air, E, is less than subsaturate or less than saturation. And if it's greater than E sub S, it's subsaturated. Now it turns out for water, this is convenient. The saturation vapor pressure has two important properties. It's a monotonic function of temperature. So as temperature increases, E sub S increases. And it only depends on temperature. So if we know the temperature, then there's a one-to-one relationship to the saturation vapor pressure. And that one-to-one relationship we call the Clausius-Clapeyron relationship. And this is just, if you think back to you probably have seen a diagram like this in a chemistry class, which is a phase diagram for water. Just shows you the kind of equilibrium states of water at different combinations of temperature and pressure. Water turns out to be a unique substance in Earth. I shouldn't just say in the atmosphere, but in the Earth system, because it can exist in solid, liquid, and gas phase. I think I read recently that on Titan, one of the moons of Saturn, methane has the same property, so you can have liquid, gas, and solid methane. So you can have a hydrologic cycle on Titan, but with methane instead of water. Relative humidity then is just a common way that we benchmark saturation. So if we know the vapor pressure E, divide by the saturation vapor pressure E sub S, that's the relative humidity, which is kind of commonly given in weather forecasts. And one of the reasons we kind of care about it in a sense, I mean, there are lots of reasons to care about it, but if you have a weather forecast that calls for high relative humidity, that might give you what we call the heat index. It's kind of a convolution between the air temperature and the relative humidity because of the kind of human physiological response to ambient conditions. In other words, if the relative humidity is too high, that kind of limits the human body's principal cooling mechanism, which is evaporation. So that's why you feel uncomfortable and you shouldn't exercise and do very strenuous things if you have combinations of high relative humidity and temperature. And then just to kind of close the circle, we define the mixing ratio. We can also define the saturation mixing ratio, which is essentially taking this thing and plugging in the saturation values. Now, if we look at W sub S, its functional dependence, it depends on temperature through the dependence of the saturation vapor pressure on temperature and the pressure. And so then you can think about the following. If we have a parcel of air that we displace upwards adiabatically, we know that its temperature decreases, and by virtue of displacing it upwards, it's moving from higher pressure to lower pressure. So the temperature for an adiabatic upward displacement, the temperature decreases and the pressure decreases, so the numerator here decreases and the denominator decreases. And so you might ask yourself, you know, since temperature is decreasing and pressure, the decrease in pressure because it's in the denominator would cause the saturation vapor pressure to, or the saturation mixing ratio to increase. Which of those changes wins out? It turns out it's not very straightforward to see. You have to go through quite a bit of algebra. But if you do that, it turns out that temperature almost always prevails. And so for an adiabatic displacement, essentially what that tells us is if we displace a parcel high enough in the atmosphere because temperature wins out, eventually the saturation vapor pressure is, or the saturation mixing ratio is going to drop far enough that for any non-zero mixing ratio, the parcel is going to become saturated. Okay? Now, that's all been a bit theoretical, so how do we kind of bring things back and make them a bit more applied? And the way we often, the intersection between thermodynamics and kind of meteorological practice tends to happen in terms of these diagrams. There are various kinds. This diagram, called a Skew Diagram, is basically a convenient way of plotting thermodynamic quantities of interest. And, you know, there's lots of information embedded within the Skew diagram. We can basically represent things, so like, for example, isotherms, lines of constant temperature, these black slanted lines. We can also plot dry adiabats, basically lines of constant potential temperature that correspond to an adiabatic process that's dry. It turns out we'll see this in a moment that, the yellow ones are the dry adiabats, so those are these lines, kind of hard to make out. The purple ones are called pseudo-adiabats. Essentially those are what happens, those are the adiabats we consider when we have a moist process. And then we can plot on top of that thermodynamic data. So the red curve here is a temperature profile that was estimated, for example, from a balloon that was launched and measured the temperature as a function of pressure. Also plot conveniently or commonly on Skew diagrams the dew point. And so that leads us to the dew point. So the dew point temperature T sub D represents the temperature to which an air parcel would need to be cooled, assuming some fixed vapor pressure, in order that saturation should occur. So if you have a sample of air that has a vapor pressure E and ambient temperature T, and it's subsaturated, the dew point temperature is the temperature to which you'd have to drop that sample of air in order that it has a relative humidity of 100%, becomes saturated. So dew point temperature and relative humidity are related to one another. Meteorologists turn out to prefer, especially in terms of representing things on Skew diagrams, prefer dew point temperature because you can put it in the same units as temperature. And it gets its name dew point temperature because that's basically, if the temperature drops to the dew point, that's when condensation occurs. So it gives you an idea. We often talk in terms of a dew point depression, so how far is a particular temperature from the formation of condensate. Now with the Skew diagram and these concepts that we've been talking about, we can now introduce a little bit more of interest to the convection problem. And so the first thing we want to talk about here is a quantity or characteristic of atmosphere called the lifting condensation level or lifted condensation level, LCL. Essentially, the LCL is the level at which, pressure level at which a parcel of air would need to be lifted in order for saturation to occur. There are numerical ways of approximating the lifting condensation level, but if you have a Skew diagram, you can estimate or you can determine the lifting condensation level graphically. So here we have a temperature profile, this kind of segmented black curve, the dew point temperature. So to find the lifted condensation level, we basically start at the temperature at usually we start at 1,000 millibars of the surface, and we imagine taking a parcel of air at the temperature, lifting it dry adiabatically up so its temperature drops. We follow that up, that's the red curve. Then starting at the dew point temperature, we basically follow one of these lines of constant saturation mixing ratio. So remember, or as long as we don't have condensation occurring, the mixing ratio is conserved. So basically we can follow the dew point temperature up along a saturation mixing ratio line. And that essentially tells us for a given mixing ratio how the dew point temperature changes as a function of height. And so where those 2 points intersect, that's where the LCL occurs. Okay? So the LCL defines, effectively, in many cases, if you can locate the LCL, you can locate the cloud base under forced ascent or free convection. Now, question you might ask is, we talk about lifting a parcel to get it up to its LCL, so how would the parcel get from the surface up to the LCL? It turns out if you look at this from the point of view of the buoyancy arguments that I was talking about earlier, this parcel would actually have negative buoyancy. So on its own, a parcel that starts at the surface would be negatively buoyant under this kind of profile. So there has to be some lifting mechanism. It could be a front, it could be a cold pool that's basically coming out. Dave will talk about that probably on Thursday. It could be a cold pool that's basically coming out and forcing a sand out ahead of it. So, that becomes an important part of the convection story, is what's kind of providing the initial lift to get up to this point. So then what happens to a parcel as it moves through its LCL? So what's going to happen with further ascent? So remember, below the LCL, it's subsaturated or unsaturated. As it moves through the LCL, then it passes that saturation point. So then you start to have water vapor within the parcel condense. That becomes very important because that condensation process, basically you have the more energetic vapor phase condensing into the less energetic liquid phase. That's releasing latent heat of vaporization. And so that latent heating that comes from the condensation process, if we kind of make an assumption that latent heating kind of stays within this parcel, this imaginary thing, then even if the parcel is being lifted and it's cooling, because it's getting this influx of the air within the parcel is getting this influx of latent heat energy, that's causing its temperature to decrease less than dry adiabatic. So the point here is that we go from a situation below the LCL where the temperature of the parcel is evolving along a dry adiabat 10 Kelvin per kilometer, above the LCL with the presence of this condensational heating, the lapse rate falls below dry adiabatic. In the interest of time, I'll probably skip for the moment through equivalent potential temperature, other than to say we can define a quantity that looks a lot like what we were talking about before in terms of potential temperature, but we fold in the effect of this condensational heating. This is what we call the equivalent potential temperature. The take-home message here is really that if you have a parcel that has a potential temperature theta and some specific humidity, the way we define this potential temperature theta sub E, equivalent potential temperature theta sub E, is you imagine all of this specific humidity, all of this vapor condenses out. And so you'd have a dry parcel at that limit that has a higher temperature, theta E, the equivalent potential temperature, because of this condensational heating effect. And graphically, the way you can determine the equivalent potential temperature is, again, you locate the LCL. Once you're above the LCL, the parcel follows a moist adiabat. Follow that moist adiabat up somewhere very high in the atmosphere, 200, 300 millibars. These moist adiabats asymptote to a unique dry adiabat. So once you've found that asymptoting dry adiabat, you follow that back down, and that's essentially the potential temperature along this dry adiabat is the equivalent potential temperature of that parcel. And a bunch of math allows us to find this moist adiabatic, technically pseudo-adiabatic, it's just a minor distinction, but the pseudo-adiabatic or moist adiabatic lapse rate is related to the dry adiabatic lapse rate, but then multiplied by this factor that depends on specific humidity and temperature. And if you do an analysis of the magnitude of this, these terms multiplying gamma sub d, turns out to be less than 1. So that tells you that the moist adiabatic or pseudo-adiabatic lapse rate is less than the dry adiabatic. Now it turns out in terms of the stability analysis that for moist stability, we now have 3 possibilities. We can have a situation which is absolutely stable. So if the environmental lapse rate is less than the moist adiabatic or pseudo-adiabatic lapse rate, it's absolutely stable. If the if the environmental lapse rate is greater than the dry adiabatic lapse rate, that's absolutely unstable. But then we have this situation in the middle when the lapse rate is between moist adiabatic and dry adiabatic, which is conditionally unstable. So it's stable with respect to dry adiabatic displacement, but unstable with respect to moist adiabatic. In terms of convection, a quantity of interest that we'll focus on more later in the week is what we call convective available potential energy, or CAPE. So simply put, CAPE, you can think of this as the energy reservoir. It's a potential energy, the energy reservoir that drives deep convection. We define CAPE conventionally in terms of a vertical integral over the buoyancy field, and the limits of integration are hard to read here, but the limits of integration go from this value z sub LFC. I forgot to mention, that's called the lifting condensation level. Lifting condensation level, so imagine that we follow a parcel up to its lifted condensation level, and then it continues to ascend. But you'll notice in this profile that it's continuing to ascend in a region where it's to the left of the environmental temperature profile. So in terms of the buoyancy, the parcel, even though it's gotten to its saturation point, it still has negative buoyancy with respect to the environment. So if you imagine there's some process here that's lifting the parcel, and then that lifting process goes away, the parcel would sink back down. But if the parcel manages to get up to this point, the LFC, now you can see that the moist adiabatic temperature lies to the right of the environmental temperature profile, so that implies positive buoyancy. So once a parcel reaches this magic level, the LFC, now it becomes positively buoyant with respect to its environment. And if you remember from our stability analysis, a parcel that gets there would just start to accelerate upwards. So CAPE is taken as the integral from the LFC up to this level, which is called the equilibrium level, or the level of neutral buoyancy. So these moist adiabats, or moist pseudo-adiabats, always curve off to the left like this. Eventually, the temperature profile of the environment is going to curve up like this. I mean, if you go all the way up to the stratosphere is inverted, so the temperature increases with height. So eventually you're going to reach this point where that parcel is going to again change its sign with respect to buoyancy and become negatively buoyant. So you can think of this kind of level of neutral buoyancy at the top would be where you'd find the top of a cloud, approximately. So CAPE is just basically calculating the part of the buoyancy, which again we can think of as the difference between this temperature curve and this one, calculating the part of the buoyancy where that's positive, okay? We define another quantity which you can think of maybe as the negative of CAPE, which we call the convective inhibition. Convective inhibition, I mean, there are different ways of defining it, but it's essentially this blue region down here. It's essentially the part of the vertical profile where the parcel would be negatively buoyant with respect to the environment. So the story in terms of the way we often think about convection is you have this kind of barrier, this convective inhibition that needs to be overcome, and the cape, if you can overcome that convective inhibition, the cape is kind of the energy that's available to drive the convection. Cape has a nice interpretation because it's potential energy. We can think about converting that potential energy to kinetic energy. And so there's a simple relationship just from energy conservation that if we convert all of the cape, all of that potential energy to vertical velocity, this gives us an estimate of the updraft, basically how fast air is ascending through convection. But you'll notice it's W max, it's the maximum convective updraft velocity. So it turns out, and we'll talk more about these things later in the week, if you consider realistic conditions, this estimate of the vertical velocity is going to be maybe a factor of 2 too high, because there are going to be factors that modify this convective available potential energy, or factors that make it not possible to convert all of the cape within a profile into updraft. Cape in thunderstorms, just to give you again a benchmark measure, you might have a kind of moderate thunderstorm of 1,500 joules per kilogram. That's the potential energy per unit mass. If we talk about thunderstorms like we have in the Great Plains of the US, you might talk more like 4,000 joules per kilogram as a really severe thunderstorm. Even if we have one of these moderate thunderstorms, 1,500 joules per kilogram, this W max would be 55 meters per second. So if you think about the kind of normal fair weather state of the atmosphere, we often don't think about the vertical motion field in the fair weather atmosphere, but if you have an updraft of even half of this, if this is 28 meters per second, you can understand why planes don't want to fly through disturbed convective weather when they're dealing with these very intense updrafts. A point to note here with respect to convection in the tropics, at least with respect to oceanic convection, which is how we've developed a lot of our theoretical understanding, is that cape values tend to be pretty small, relatively speaking, in the tropics. And as a consequence, we have lower convective updraft velocities over the tropics vis-a-vis kind of our other model of convection, which would be the mid-latitude summertime convection.
Excuse me, Ben.
Yeah.
Is that vertical velocity measurement representative of some part of the cloud that is moving up? Or is it some just...
Yeah, that would be, so there's... that's obviously an idealization. We kind of have this model of some plume of air mass that's kind of rising, but there's actually rising motion and sinking motion that's kind of happening throughout the convective environment. So that would sort of be a maximum somewhere within the sort of center of convection, even if not the entire, column of convecting air is moving at that velocity. And obviously, as we'll see kind of in tomorrow's discussion, what convection essentially does is consumes cape, right? So as the convective process unfolds, the cape decreases, that convective available potential energy gets converted. And so, at some level, it's almost like if you could convert it instantaneously to updraft, that's what you would get. So that's part of the approximation as well. So 2 other quantities to define, not doing too poorly on time, to define for later reference are what we call dry and moist static energy. Have them, dry, that should be bold-faced. Dry static energy is basically a combination of Cp, the specific heat at constant pressure, times the temperature field, plus potential energy per unit mass, G times dZ. So it's basically the energy, the kind of dry energy of a parcel of air within the atmosphere. And the moist static energy, we take the dry static energy and add the contribution from the potential condensational heating. Okay? It turns out S and H are related to things that we've already seen. S is related to the potential temperature theta. H is approximately related to theta E. So to see that, if you take the Poisson equation, which tells us how theta depends on pressure, take the log of it, you get this thing, compute the differential of the log of theta, take the differential of this thing, you get this, and that's just, if you take the differential of the dry static energy, ds over Cp. So Cp times d ln theta is just equal to ds. The reason for pointing that out is that we know we've said that potential temperature is a conserved quantity for a dry adiabatic process. So by this relationship, S is also a conserved quantity. H is approximately conserved for a moist adiabatic process. So I think with that, I'm at the end of the review of thermo. So should we take a break, or 7:00 or 6:06?
Do you guys want to take a quick break? Cafe? Okay. Let's do that real quick and then start on the next. Okay. Yeah, that was good. That was good. Not too much, not overkill.
Good.
Really good sample.
Boy, I'm going to need to see about that thing with the I know that guy back there. The infrastructure.
Oh, yeah.
Because put that off before I say something that I'm going to get in trouble for.
Yeah.
If I have to get the department support, and they're going to say I'm supporting this infrastructure proposal, then I'm shit out of luck. I'm not going to. I mean, time.
Yeah.
Let me run real quick and see if I can find the department head. She's probably not here right now. But I'll be right back.
All right. Did
you want a cookie or coffee?
I'm going to get some coffee. Oh, sorry.
¿Qué pasó, David?
Sí, pues básicamente la declaración fue bueno, la curva de abajo que seca y la curva pero ya pues es lo que
So you want to get started again?
Yeah. Oh,
We've got, I mean, this is Mexico, so we can be a little bit lax.
no, that's
Do
fine.
you want a cookie?
No, I'm good.
Lo que quería comentar, alguien me preguntó, todas las notas las vamos a subir y aparte si están teniendo problemas en seguir lo que dice, hay video en vivo ahora y pues lo vamos a tener así grabado, porque pueden ver las notas y escuchar lo que está diciendo de nuevo, digamos. Eso no quiere decir que voy a eliminar eso, pero tendrán otra posibilidad. Por eso va tan rápido, porque él sabe que tienen acceso a las notas. Okay. Pero no como digo, no tengan miedo de parar y preguntar.
Oh, and I'll also make sure to have my email address and things if people have questions. And
Right.
well, welcome back. I'm glad I only scared off a few people. Maybe they went out. I don't know. What time do you eat? What time do you eat dinner? What time is dinner, Dave?
What time is dinner?
Oh, so we have hours, right? We have hours. Okay, we're good. I'm not sure. I was shoveling snow yesterday, so I'm not sure that I have hours. But so, in the second part of today's lecture, I want to talk do a little bit of a survey of convection in the tropics. And again, you know, this can't be an exhaustive coverage of things, so you won't see tropical cyclones, although they're very important. But just to give you kind of a flavor of some of the phenomenology that I'm interested in and Dave and Kathleen are interested in. And I just wanted to start off by showing you these two different maps. Actually, I should mention here, COMET, when you see the slides say COMET, there's a nice textbook that's been produced by the UCAR, the University Corporation for Atmospheric Research in the US, has an educational program called COMET, and they have a nice textbook on tropical meteorology, it's still free. I've heard that it may not be free forever, but you can go and download a copy of it. You just have to register your email address. So a lot of the figures that I'm showing are actually from the COMET textbook. This map at the top shows, these two maps actually show different sampling campaigns. Much of our interest in tropical meteorology really came about through this kind of observational work that many folks did starting back in the maybe late 60s over here maybe even earlier in the Western Pacific, extending on through today. And I just wanted to put this up here in part because, you know, when I first started looking at the field and people would talk about Toga Core or Quajex or whatever, I had no idea what they're talking about. But these specific field campaigns that, you know, have become quite famous in their own right. So some of the results that I'll show are kind of leveraging on these field campaigns. And what I wanted to talk a little bit about first, it's kind of hard to make out some of these figures, but just to kind of give you, since we've talked now about thermodynamics, introduced some of the basic concepts or reviewed some of the basic concepts, to actually see what thermodynamics look like in the tropics as kind of the background for understanding convection. And this is, the first set of figures here are profiles of relative humidity. So basically on the x-axis, relative humidity in percentage as a function of pressure. So these are from various field campaigns in the Caribbean and the tropical North Atlantic. And this early one from Jordan, 1958, is kind of the canonical example, I mean the earliest one, kind of showing what the relative humidity profile looks like. And the point of showing some of these other figures, I mean they're all showing essentially the same thing, is just to show you both how, if we go to different places in the tropics, equatorial, West Pacific, tropical, East Atlantic, you can see some similarities in the relative humidity profile. So we have the decrease in relative humidity as you go up, maybe a kind of local maximum in relative humidity just above the surface. But also to point out that there are important differences in the thermodynamic environment in the tropics. You know, we might often think about the tropics as being relatively warm and wet compared to high latitudes, but there are substantial variations. One of the interesting ones is kind of in this panel here, showing two relative humidity profiles from the tropical North Atlantic, sampled at under different large-scale conditions. SAL here means Saharan air layer. So basically, this sampling campaign was kind of targeting the effect of dry air outflow coming off of West Africa into the Atlantic. And what you'll notice is you have a very, relative to this kind of baseline profile from Jordan 1958, pretty substantial variation in the relative humidity environment in the Atlantic, depending on whether you're sitting in the Saharan air layer, which is very dry in the mid-levels, or in the non-Saharan air layer. And so those kind of thermodynamic differences can be quite important as you move from place to place or from one large-scale regime to another. This is again kind of the same overview, but now looking at equivalent potential temperature theta sub E. And again, kind of if you look in a textbook of tropical meteorology, you'll probably see this set of theta E. This is theta E here in the middle. Theta E star is basically the theta E profile, but evaluated at the temperature at which saturation occurs, or evaluated, it's the saturation value at the temperature of the sounding. So, you can kind of see here a sort of, and there's the theta profile, the characteristic of the theta E profile is this minimum in theta E. So basically, you have the effect of theta, which is increasing with height, and then, if you think about the relative humidity, but also the specific humidity is decreasing with height, and theta E is a convolution, essentially a convolution of the two. So, you get this local minimum in the mid-troposphere because of the decrease of one and the increase of other with height. And this, again, is kind of the sort of canonical example that people show, but again, to point out that in this case for non-Saharan air layer, air tends to be moister in the mid-levels, and then when, the sampling is done within one of these dry air, dusty outflows from Africa, you tend to see much lower values of theta E in the mid-troposphere. And we'll see actually that mid-level theta E turns out to be very important in its relationship to convection. This is a comparison of thermodynamic differences between convective and non-convective or fair weather conditions. So looking at three different thermodynamic quantities of interest. So the dotted line here is the actual temperature. The mixing ratio is this one, dashes, yep, and delta theta E. So these are differences between convective and non-convective. And so in terms of the temperature environment in this particular set of data, there's maybe a little bit of elevated temperature in the upper troposphere during convective events relative to non-convective, but for the most part, the temperature profile is pretty much the same. The moisture profile in terms of the mixing ratio, it tends to be quite a bit moister under convective conditions than under fair weather conditions, and that's reflected then in the difference in theta E, where you have this very pronounced mid-level difference in theta E, largely accounted for by this difference in mixing ratio. And here's another run-in of looking at theta E, but now it's taking theta E profiles and classifying them, and I can't remember the details of how this was done, but effectively sorting them by rainfall amount. This is done for sampling at Barbados in the Caribbean. And basically the Roman numerals here correspond to different categories of precipitation and convection. So one is, again, I don't remember the details, but going from weaker to stronger convection or precipitation. And basically what you see is that in this case, at say 700 millibars, where you have this delta theta, or where you have this theta E minimum, that as the profiles are sorted according to convective activity, that you can see that that minimum tends to get shallower, okay? And so, you know, to leading order, you might kind of look at theta E at this level in the atmosphere and make some mapping onto precipitation, okay? This becomes a kind of important region of control for how intense the precipitation is.
When is the higher precipitation rates here?
These would be the, you know, sorry, this one is whatever these categories was, this was the weakest, and this was the strongest. So there's kind of a monotonic increase here in the you know, it's a less minimum if you have stronger rainfall.
But that's previous to the event during.
That's a good question.
Yeah, that is a good question. Here it was probably conditioned on some time before a rainfall event, I would guess. Yeah.
Is there any reason why it seems that the inflection point, or like when it's bending the curve, seems to be at almost the same level for all cases?
Yeah, you know, that's an interesting question too. I mean, I don't, and again, you know, I would have to go back to this study to actually look at the details. You know, how much to kind of trust, because my eye might kind of see a sort of increase, a slight increase here in the minimum, but I don't know about, you know, if you had error bars on these. I think this would be pretty robust, and actually what Kathleen will talk about a little bit tomorrow, I think, is kind of related to this. So more detail to come. So those were kind of looking at things in the vertical. Now we want to look at some quantities through time to kind of look at how thermodynamic quantities of interest evolve through a convective event. And I think this is a particularly interesting way of doing things. So this was studying a type of convective system, and I'll talk a little bit about it momentarily, called a mesoscale convective system. Basically, a lot of the convection that we see in the tropics tends to be organized in these larger scale structures instead of individual events. They tend to be part of a bigger structure called a mesoscale convective system. This particular mesoscale convective system turns out to have been a propagating system, so propagating from right to left or from east to west. And so what we're looking at here is a cross-section of height and distance relative to this leading edge of the, you know, kind of where the gust front is at the surface. So that's denoted by 0. So if you're in the environment out ahead, the undisturbed environment out ahead of this propagating system, you're over here, and in the sort of very active, intense convecting part of the system here, just behind the edge, and then kind of in this broad region called the wake, which is basically after the storm. You know, at some earlier time, the storm edge would have been here, and then it's propagated off, and then it's kind of left in this wake. But what I wanted to point out here are these kind of cross sections through this mesoscale convective system of both dry static energy and moist static energy, essentially showing how moist static energy or dry static energy in the environment out ahead of this MCS in the undisturbed environment looks compared to both quantities in the environment after the MCS has passed. And what you can see is both the moist static energy and the dry static energy drop. This idea that convection is kind of consuming these quantities and causing, through various effects related largely to downdrafts and cold pools and other things, but basically changing the boundary layer thermodynamics. And so you get this sharp drop in dry static energy and moist static energy, kind of in the active convective region, and then a relatively slow recovery, you know, as you kind of move into this wake. And then back here, you're kind of course, this is disturbed, but the environment is recovering from the passage of this MCS. And so this is kind of a characteristic signature that we see, is that you have this kind of high favorable environment out ahead of the MCS, and as a result of the MCS, it modifies the thermodynamic environment, causing both these quantities to decrease, and then the environmental factors cause the slow recovery. And that'll be kind of a, yeah.
Do you always consume the same amount of dry static energy as wet static energy? I mean, these consumptions during the process are.
Yeah, I think it's gonna depend on what the convection is like. The fact that they were kind of on the same scale there, is that what you're talking about?
Yeah,
or?
that's right. I mean, the drop is very similar, but
Yeah,
if there is something interesting to say, one is little smaller to the other.
Presumably, I don't know, Dave, if you have any.
I would think it has, I mean, a lot of people talk about the boundary layer being dried out by cold pools, but I'm not sure that's always the case. I think that to me is more iffy. So it's going to be, I think it's going to be related to whether you're actually bringing down relatively moister air because it's raining, as opposed to what it was before. So I would assume that would be kind of what's going to control. Does that answer your question?
Yeah.
Yeah, I think tomorrow I think I have, one of the kind of theoretical ways of understanding convection is to kind of look at the boundary layer control of convection in terms of low-level theta E, and kind of developing the understanding of what processes are important for determining low-level theta E. So it's not, things like downdrafts certainly, but surface fluxes also contribute, advection. So I think it's going to depend. Yeah. Turning a little bit to the kind of moisture side of things, and partly to show, I don't know in your introduction if you mentioned, but Kathleen works with David Nealon. I also worked in David Nealon's group, so part of showing this is to kind of highlight some of their work. This is a particularly nice study by David and his former PhD student, Chris Holloway, who's now in the UK, in which he analyzed a set of measurements of column water vapor from, one of the best records that we have, at least long-term records, from the ARM site, the Atmospheric Radiation Measurement Site, which at the time had a so-called mobile facility, an AMF facility, on the island of Nauru in the Western Pacific. And I'd like to show this. This is the entire country of Nauru. It's 21 square kilometers. And I think if I remember, the ARM site was over here somewhere. People talk about the west coast of Nauru, but west versus east if it's 21 square kilometers. But anyway, so for 8 some odd years, ARM was basically out here taking measurements of the thermodynamic environment in the Western Pacific. This site, unfortunately, at Nauru has been decommissioned, although there are still 2 other Western Pacific sites that are taking measurements. But Chris was able to kind of leverage this long data set, 8 odd years of data, to kind of develop some nice statistics between the relationship between convective events and moisture, and produce these very nice plots, which the details here are not really important, other than to say he selected a number of strong convective events on the order of 300 or so, which he placed at time t equals 0, and then looked at the relationship of the moisture field relative to time t equals 0. So moisture, in this case, in terms of column integrated water vapor, so how much water vapor there is in the column of atmosphere leading up to those precipitation events, so that's to the left, and then after the precipitation events. And what's particularly nice, I think, about this kind of plot is that you see this kind of slow increase. This is column water vapor on this axis. So going from value around 50 millimeters up to a maximum here. And again, it's an average, so it kind of smooths out. You might have larger values than what's shown here, but in the average, up to about 56 millimeters. But you see this kind of slow increase, maybe starting 48 to 24 hours in advance of these heavy convective events at Nauru. So you can kind of think of that as a synoptic scale moistening of the environment, maybe as a tropical wave is propagating toward Nauru from the east. And then, within 12 to 6 hours or so before the initiation of the strong convective event, you have this you see this jump in the slope, this increase in the slope. So much steeper increase in column water vapor leading right up to the events. And Chris and David sort of speculated that this was due to mesoscale organization. So you have this kind of interaction of scales with synoptic scales kind of providing this moistening environment in which these events are embedded. But then at smaller mesoscales, which is actually where the convective organization is taking place, that kind of the organization of convection as it's getting its act together around Nauru is what's causing this increase in column water vapor right before the event. And then, of course, precipitation is a sink for column water vapor. So after the occurrence of the event, the column water vapor drops off as it's raining out of the column. Yep.
Do you need, I mean, does that upper panel shows that you need some kind of synoptic forcing from, with water vapor to get that thing at the end, to get that mesoscale increase always?
This is like 300 events. So, if you did some further sorting of the events, maybe you'd see some that are just more mesoscale, some that have this, I actually did some follow-up work on this, kind of looking for these larger scale structures. And if you kind of compare the column water vapor signature at Nauru to some gridded product, you can kind of see some propagation coming along. Although I never sort of sorted the events, to say which of the high column water vapor events were associated with the passage of a wave or not. I imagine you could have both kinds. Because, and that's one of the points of the story, is that the convection in the tropics organizes on many different scales. Kathleen will talk a lot more about this in her part of the lecture tomorrow, but just to say that some interesting work that's come out of, it started actually with David Nealon and a postdoc at the time, Ola Peters, or I think he was maybe a visiting scientist. But essentially what they wanted to do, Ola Peters comes from a background in statistical mechanics, and he wanted to apply some of the architecture of statistical mechanics concepts like self-organized criticality, which again we'll talk a little bit more about tomorrow, apply those in the realm of atmospheric science. And they came up with this really nice analysis, which is really only possible by having a wealth of observations from satellites, which basically give us instantaneous retrievals of precipitation and column water vapor many, many times over. So in order to kind of develop these statistics, you tend to need large numbers of observations. But what they did by sort of carefully sorting the data is showing a relationship between column water vapor and precipitation rate. And so what you can see here in these curves, and there's actually models on here as well as observations, but the TMI is the observation. So these curves here that kind of tail off like this, those are the observational curves. So you can kind of see the increase that there's this, at low column water vapor, a tendency for low precipitation rates to occur, and then at higher column water vapors, you can see this steep pickup in precipitation rate. And this, and again, we'll talk a little bit more about the details tomorrow, but kind of has led to the suggestion of a critical value of column water vapor that kind of governs this transition between weak precipitation or weak convection over here and strong convection over here. And again, what's kind of nice about this is it borrows from this wealth of literature that exists in the statistical mechanics community and really kind of maps it on to this real world problem. Another interesting thing too is, and there's another nice way of showing this, and maybe Kathleen has that in the talk, but this sort of critical value of column water vapor is actually, under the right conditions, you can show that it's a function of some deep layer tropospheric temperature. So if you do a rescaling of the critical water vapor by tropospheric temperature, you can basically show that these curves all sort of collapse onto one another. So right now they're all sorted by this kind of layer average tropospheric temperature. And if you do the rescaling by the critical water vapor, then they all collapse onto the same thing. So it's kind of a nice demonstration. So I just kind of stuck this in here to get back to some of the earlier thermodynamics that we talked about, just to kind of, I didn't just do that for fun, but but to say that when we talk about a kind of model of convection as kind of a, individual cumulonimbus, thunderstorm type of thing, we can kind of map those thermodynamic quantities like the lifting condensation level, the level of free convection, and the equilibrium level into this diagram. So the equilibrium level here, where again, in the parcel view is where you change from positive buoyancy to negative buoyancy up above. That's kind of where you have the top of the cloud. Down here, they don't actually have the LCL shown on here, but the cloud base is essentially, tends to occur near the LCL. And the level of free convection, again, is this region where parcels are positively buoyant with respect to their environment and freely accelerate upwards. And that's really, it's really under those conditions that you see this kind of intense development of convection when parcels are actually able to access that region of positive buoyancy. And just to kind of point out the other side of the story, we tend to be interested in convection in the tropics because of its relationship to precipitation. So, you have this air mass that's ascending through these cumulonimbus clouds, condensing. There's microphysics going on, and, don't ask me about microphysics, but microphysics causing the generation of hydrometeors, and those hydrometeors eventually fall out. That's what we get as rainfall. But then some interesting kind of things happen as the rain starts to fall through the cloud, generates kind of the downdraft side of the story. So we were talking before about convective updrafts, but the generation of convective downdrafts turn out to be very important in terms of the overall dynamics of convection, and Dave might talk a little bit more about this. One of the effects of these downdrafts is basically they're resulting in, again, without going into the details, bringing relatively cold and dry air back down into the boundary layer, forming this structure at the surface called a cold pool, basically a region of very dense cold air that once it hits the surface, hits a hard boundary, it starts to expand out laterally. And, at kind of this phase of in this phase, you basically have a little cumulus congestus start to grow up into this big cumulonimbus. Then it starts raining, and kind of in this illustration, that process of forming convective downdrafts and the associated cold pool kind of kills off the convection, okay? And so, you basically have this convective element grow up, form downdrafts and cold pools, which kill it off. Now, it turns out this kind of view of convection in terms of, sort of isolated cumulonimbus isn't really the way most of the rainfall that we see in the tropics occurs. Rather, most of it tends to be in more organized, by which I mean larger scale structures, called mesoscale convective systems. And, this is kind of a satellite image over South America, showing these kind of larger features. These are much bigger than, the individual scale, 10 kilometer or so, that you might expect for individual thunderstorms. They tend to be much bigger in scale, so much more organized at larger scales, on the order of 100 to 1,000 kilometers. And, whereas an individual convective element or convective thunderstorm might last for an hour or so, mesoscale convective systems might persist up to a day or even longer. And so our understanding of convection in the tropics, in order to understand convection in the tropics, we really need to understand these kind of larger scale structures. And this is kind of a nice example, again, from my favorite website, showing a mesoscale convective system developing over the Amazon. This is just to point out that when we look at mesoscale convective systems in the tropics, there's a distribution of sizes and lifetimes. It's basically a kind of plot showing the distribution of mesoscale convective systems as a function of their lifetime and their maximum size. So, many mesoscale convective systems are sticking around on the order of a couple of hours, maybe at scales of 100 kilometers. You do have some, although they tend to be relatively infrequent, that might last, again, close to a day, and with size scales that are maybe 300 to 500 kilometers. So we have to have a way of accounting for this kind of larger scale structure. So what we've largely developed so far in this lecture in terms of the thermodynamics of convection really is kind of this view of individual convective elements, maybe a single thunderstorm. How do we kind of account for the larger scale structure in the MCS? And it turns out the story, and again, MCSs are not my cup of tea. It's complicated, as many things are. That really, to form MCSs, you can think about starting from individual convective elements, convective thunderstorms, but there need to be ingredients in place in order for them to organize at these larger scales. And kind of an important process that's often discussed is this idea of layer lifting, which is basically taking a layer of air that's conditionally unstable at low levels, and through some process, this lifted layer of air kind of helps to organize the structure of the MCS. And again, I won't go into the details because I can't really do it justice here, but just to say that the process for organizing MCSs is a complicated one. What I do want to point out is that in terms of looking at precipitation in MCSs, we distinguish two types of precipitation, so convective and stratiform. So the convective precipitation, tends to be what we associate as the more intense, you might say the more active convection, and the stratiform precipitation tends to be weaker in intensity. And in terms of the structure of the MCS, if you imagine here we're looking at a cross-section, and earlier I showed the propagating MCS, kind of has this region of intense convection kind of concentrated near the front of you imagine this MCS kind of propagating along, this active convective part here, and then a very broad region kind of in its wake, which is where we find the stratiform precipitation. And again, things are complicated. This is kind of a schematic from Zipser showing the sort of detailed anatomy of an MCS, just kind of showing these different elements. So, we have boundary layer, active convection kind of with these updrafts and downdrafts kind of forming in this region of very active convection. You have a layer of air, environmental air, that's being entrained into this MCS. All of these things, the circles here kind of tell you I think that's the equivalent potential temperature. So you have high equivalent potential temperature here and lower equivalent potential temperature here. This region of very active convection with strong updrafts can kind of deliver this high equivalent potential temperature air very high up in the atmosphere. And so, this kind of comes to some things we'll talk about tomorrow, which is, how do we actually move, how does the air mass here actually move up here, and how is it modified as it moves from the surface up? One of the assumptions is often that we just take this kind of air at the surface and kind of transport it up without any interactions with the intervening air mass, but that might be true kind of if you're in the middle of this large-scale structure, but we have other important processes, namely the idea of entrainment, which is that as this convection is moving air masses upwards, they're also experiencing mixing with the surrounding environment. And that's going to change their thermodynamics. Just kind of, again, this is a simple cartoon kind of showing how, and again, the details here are not very important other than to say that we can start with one of these individual convective elements, starts to modify its environment in the presence of the right kind of environmental forcing. If we have this interaction with this kind of lifted layer of air, that can start to organize the convection into this bigger structure, which becomes the MCS. MCSs, just to kind of point out, what might be obvious is that they don't just form and then stand still, that we see them propagating around. And the propagation characteristics of MCSs can be quite interesting. So this is a type of plot called a Hofmüller plot, which in this view shows time increasing on this axis as a function of longitude. And so you have, I think this is from the Pacific, so the Western Pacific, a propagating MCS that you can see that this propagating MCS actually lived for quite a long time. It started kind of in the middle of the day here, persisted all throughout the next day. But it didn't just, it formed somewhere over here and then propagated off to the west. This kind of cluster of things over here kind of suggests an MCS that maybe started at one point, and then you can kind of see an MCS that kind of propagated down here, but maybe also bifurcated. So you can have MCSs that interact with one another, MCSs that start as a single entity and then split. Maybe here's another example of a bifurcating MCS. So that, you know, the propagation characteristics and the time evolution can be quite complex. So to get back to this distinction of convective versus stratiform precipitation, so if we distinguish convective precipitation, again, the very intense precipitation, from stratiform, we see important differences. So convective precipitation rates are typically 3 to 6 times larger than stratiform rates. So in this table, convective rain rate kind of on average for the whole tropics might be 7.3 millimeters per hour, stratiform 1.8. So rain rates in convective rainfall are much higher than stratiform. The area of stratiform rainfall, so if you kind of look at this kind of as the sort of number of pixels that would be occupied by stratiform rain, that tends to occur over a larger areal fraction. So the overall fraction, when you kind of convolve the rain rate with the area, the stratiform rain fraction is maybe 40% of the tropical rainfall, so the remaining, not quite 60, but most of the rest of it is convective rainfall. Convective rain rates tend to be higher over land compared to ocean, maybe a factor of 2. 3/4 of the areal fraction of rainfall in the tropics is stratiform as opposed to convective. So convective rainfall tends to be more intense but more concentrated. And this is just kind of a map. This was from a study by Courtney Schumacher and Bob House, showing kind of on a pixel by pixel basis where you have stratiform rainfall occurring and where you have convective rainfall occurring. So we often, of course, where we have convective rainfall is where we also tend to see stratiform rainfall, particularly if you think about this in terms of MCSs, that the MCSs have both this convective part and the stratiform part.
Excuse me,
Yep.
stratiforms are low clouds that we see in the GOES images?
Yeah, I think, I mean, how they actually define stratiform here, I'm not quite sure what the operational definition is, but mainly I think of it more in terms of this difference in the intensity of the rainfall. Obviously, the cloud structure, the thermodynamic structure is going to be different too, but to leading order, I think it's the intensity difference.
Ben, I don't know, are you going to talk a little bit about how it relates to the heating profiles, that they're fundamentally different from isolated?
Probably. I don't know if I'll get to that tomorrow, but
It's in the lecture, I don't remember if I saw it.
maybe Wednesday. Yeah, I can't remember.
Because then you could also put that in the context of how models have difficulties in organizing
Right.
convection, and that which is critical to how the atmosphere, the tropical atmosphere actually adjusts itself.
Right. Yeah.
Okay.
This also from Schumacher and House, kind of distinguishing a third type of precipitation, which they call shallow convective. This kind of shallow convective rainfall typically isn't associated with MCSs. This is more like isolated cumulus clouds. And, you know, if you remembered from the other map, if I toggle back, where you have this kind of convective or stratiform rainfall, you kind of see it in these places, and I'll talk a little bit more about these structures. This is kind of where we see a lot of the intense precipitation in the tropics kind of organized in these convection zones, whereas this stratiform, this shallow convective rainfall is kind of falling outside of those places. Shallow convective is generally weak and largely confined to ocean basins adjacent to these regions of more intense convection. Also, if we look at MCSs in terms of land versus ocean, we can see important differences. This is just a couple of them. So one category of MCS, the so-called mesoscale convective complex, which tend to be, you know, on the scale of intensity or the close to the most intense, longest lasting, and also quasi-circular in structure with extremely high cold cloud tops. Those types of MCSs, and it's kind of hard to make out the continental outlines here, but if you look at where mesoscale convective complexes tend to form or occur, they tend to be located over or very close to continental regions. And so this has been attributed to, basically during the daytime, the land surface can heat up more so than the ocean, generating larger amounts of low-level buoyancy. And so having that kind of those high values of low-level buoyancy seem to be especially important in forming these really intense mesoscale convective complexes. Some nice work by Steve Nesbitt kind of looked at lightning as kind of a quantity of interest related to convection and rainfall. It basically shows, from observational analysis that lightning strikes tend to be much more common over land regions than over the ocean. And this probably is largely reflecting differences in the ice particle characteristics. So over the land, you can form clouds with higher tops, tend to have a larger ice content, which tends to be, in terms of the physics of lightning, is more important. Switching gears a little bit to talk about a scale of time variability in convection, which is the diurnal cycle, and we'll talk a little bit more about this. Probably Dave will follow up with some of this on Thursday, or I'll talk a little bit about it too in the context of models. But diurnal means daily, so it's a daily cycle of rainfall. And when we look at oceanic regions in the tropics or land regions in the tropics, of course the details differ depending on where you are geographically, but as a general rule of thumb, tropical oceanic regions tend to have weak diurnal cycles, so weak variability during the course of the day and when convection occurs. And they oftentimes, even though they do have a weak diurnal cycle, there's a tendency for a maximum in the diurnal cycle close to local sunrise. Whereas over land, the situation is quite a bit different, very intense diurnal cycle and a very strong and pronounced afternoon maximum in the diurnal cycle. Again, the details, if you go to a particular point, somewhere here in Mexico or in the Amazon, the details might differ depending on the local characteristics, but kind of aggregated over the whole of the tropics. This is kind of the general story. This is just to give you a kind of overview, and the Comet textbook has some nice regional examples. I just chose one for the maritime continent, which is basically the collection of islands between Australia and Asia, basically showing different points in the diurnal cycle of rainfall. So if we start, hard to make out my one, but this is late evening. So pay attention to New Guinea. So New Guinea is an island in the maritime continent, which basically has kind of a mountain range that runs diagonally like this. And so you have a large concentration of the convection in close to the highlands of New Guinea at this time of day. Then as we move forward, that's the two, I think. Yeah, move forward close to local midnight, you can see that the high convection that was kind of centered here has now kind of split in two. And so this is basically interpreted as, kind of orographically generating this convection over the mountains, and then it propagates through kind of interactions with sea breezes and other things, kind of propagates away from the high topography toward either the northwest toward this coast or to the northeast or to the southwest. When you get to morning time over here, you can see that now a lot of the convection in the maritime continent favors the ocean rather than the land surface. So there's New Guinea, which is now over the mountains, kind of a local minimum in the rainfall. And, kind of heading into early afternoon, the whole thing sort of gets, the thermodynamics start to set up again to kind of produce this late afternoon to early evening maximum over the land surface. So, some take-home messages here. In the case of New Guinea, a big part of the story with the diurnal cycle is the interaction with the topography, but you do see this kind of general contrast between the ocean, which has the maximum in convection, in the morning, let's say, and the land surface, which has the maximum in convection in the afternoon or evening.
How are we doing then? Are we getting pretty close to this? Is that time or?
Yeah, in fact, I have, I think, 3 more slides.
Okay.
This is kind of turning to a scale of interest of mine that I'll talk about more throughout the week, and this is kind of what the precipitation, the kind of large-scale picture looks like in terms of the annual mean rainfall in the tropics, kind of showing a lot of these structures are probably familiar to you. But you have these kind of regions of, very zonally elongated. I showed the satellite image of the ITCZ earlier, the East Pacific ITCZ and ITCZ in the Atlantic. Then over the continents, this is for the annual mean, over the continents you have this kind of region of intense convection over the Amazon, not quite as prominent here, but over the Congo Basin rainforest in Africa, and then over the maritime continent. Some interesting, another area of research interest of mine is this feature called the South Pacific Convergent Zone. So it's a little bit different than the ITCZ because it has this kind of weird diagonal tilt. But the basic idea is that when we look on these timescales, kind of in the large scale sense, that we see convection organized into very large structures. And then just to, in fact, this is my last slide, to kind of highlight another aspect of the large, we've talked about the diurnal cycle, talked a little bit about high frequencies, the annual mean. Seasonal cycle is also very important, so I teach a class in tropical meteorology back in New Jersey. And of course for us, seasons, we have 4 seasons, cold, hot, not quite as cold or hot. Someone told me that spring and summer, or spring and fall, are really just statistical artifacts. But here in the tropics, as I explained to my students, the way we typically look at seasonality is in terms of rainfall. And you see very interesting seasonal cycles. This is just from the Americas. Very interesting seasonal cycles in the distribution of rainfall. So if we contrast, say, Manaus, Brazil, it has this seasonality to it with a local dry season in July and August. If we go north of the equator, the 0th order picture is kind of the inverse seasonality, so more intense rainfall in June, July, August. But it's clearly not just a matter of where you are latitudinally. So if you contrast Belém on the coast of Brazil with Manaus, you do have a dry season here, but the characteristic of the dry season is much different than what we have at Manaus. And of course, and Dave may have talked to you about this with the work that he's done in the Amazon, that the regimes, Belém is right on the coast, so has, kind of the influence of sea breezes and other things. Manaus is in the center of the Amazon where those influences are less important. Places like Kingston and Jamaica, are going to have effects due to the interaction between the islands and the adjacent ocean. Of course, here on the southern tip of Baja, tends to be very dry, but then you have this local wet season. And of course, we talk about the monsoon here in the northwestern part of Mexico and the southwestern part of the US. So a big part of understanding climate in the tropics is really understanding where the seasonality and rainfall comes from and how we relate that seasonality to the drivers, the change in insulation at the top of the atmosphere as kind of the key driver, but also the influence of the oceans for places that are close by the ocean, the effects of topography, the effects of, being over a forested region here in the Amazon as opposed to less forested as you move toward the periphery of the Amazon, so how the land surface interacts. And, these are things I hope to touch a bit more on later in the week. So I think that's it.
That's it.
Yep.
All right, thank you, Ben. A quick note, we'll start again. Pues mañana, pues, la misma hora, no vamos a llegar tarde, prometo. Por favor, pásenme de la lista, ¿no? Creo que anda por allá. Ok. ¿Se acabó?